Assalamu alaikum dear students. This is Electrical Machines Lab and today we are going to perform lab number 4, that is voltage regulation and efficiency of single phase transformer. We have already performed several tests in lab number 2 and 3. We have performed short circuit test and open circuit test on the transformer, and we got the shunt branch parameters and series branch parameters. So now we can model the transformer. We can model the exact uh, circuit on the Matlab Simulink, and we can find out the voltage regulation and also the efficiency of the transformer. Before going to the Matlab, let me first talk about what is voltage regulation. Voltage regulation is basically how much voltage you are sending and how much voltage you are getting at the output. The formula of voltage regulation is no load voltage minus full load voltage divided by full load voltage. Now, this no load voltage is the voltage that you get when there is no load connected at the output, and the full load voltage is the voltage that is when you connect a load and you get the corresponding voltage. So no load voltage is always greater than the full load voltage, because when there is no load connected, you will get maximum voltage because there is no voltage drop in that case. On the other hand, when you have the load connected, there will be some voltage drop in the circuit and you will get less voltage as compared to the no load voltage. So this is the voltage regulation. Now, why voltage regulation is important? Uh, why do we need to know the voltage regulation? It is important in the sense that if you know the voltage regulation, then you can figure out exactly how much voltage do you need to send from the source so that you will get exactly the same amount of voltage that you want to have on the output. For example, uh, the standard limit on the voltage regulation in the household is around 5%. As you know, the standard voltage in Pakistan is 230 volts. So the utility company is bound to provide you a voltage regulation of 5%, plus minus 5%. Uh, if you if you calculate the 5% of 230 volt, that is around 10 volts. So plus minus 10 volts of 230 volt is the lower limit will be 220 volts and the upper limit would be 240 volts. So K Electric is bound to provide us a voltage in the range of 220 volts to 240 volts. So if this is the standard limit of voltage regulation in Pakistan. So voltage regulation is important because if you know the voltage regulation, then you will know that exactly how much voltage you have to send from the input so that you will get the corresponding output voltage at the receiving end. Okay, so let's get started. On Matlab, we have to make this circuit. We already know these parameters. We got the values of these parameters in lab number 2 and lab number 3. Okay, let's make this circuit. Okay, we need voltmeter and ammeter. We also need AC voltage source. So this is the AC voltage source. We also need RMS block, display block, okay, we also need to go to and from blocks. So add these two, from and go to. We also need power block. actually RLC branch. Here is the RLC branch. When you double click the RC branch, you can make it RL or C or any connection, any combination of these. You can rotate it like this. Okay, that's that voltmeter. Set it to 50 volts. We should have this voltage 0. Okay. The power of 50. And the motor is 120 into square root of 2. That is the harness voltage. Okay. So this is the input power. This is input current, and this is input voltage or primary side voltage. These are the series parameters. Make it L. We will set the values later. Okay, so these are the series parameters. Now we need to connect emitter. this is a load. This is the go-to block. Let's add this go-to block to this secondary voltage. This is V2. Okay, and this is secondary current I2. Okay. We also need the power block for the secondary side. Okay, voltage. Get the voltage from here and current from here. That's it. Okay, so we have made this circuit as shown here. Now we have to enter the values of these parameters that we have from lab number 2 and lab number 3. So go to lab number 2. So here we have the value of RC and XM. Okay, one thing to note here is that we perform the lab number 2 and lab number 3 on the high voltage side, on the primary side. So we have to refer these values to the secondary side of the transformer. So we have to divide all the values, these values and these values. We have to divide all these values by a square so that these values are referred to the secondary side, because we perform the tests on the primary side, high voltage side, that is the primary side. So you have to divide all these values by a square. I have already done this. So this is the value I have to enter, RC for RC. So here is my RC. Remove the comma. Okay, and for inductance, so we have to enter the value of inductance, not reactance. So you have to convert the value of reactance into inductance. You know that formula of reactance, x is equal to 2 pi f into L. So we have to divide the reactance by 2 pi f. (50 Hz is frequency. So x divided by 2 pi f is equal to L. Okay. Now go to layer number 3. So I have already referred the values to the by dividing it by a square. So this is R equivalent 1.8 and this is x equivalent 53.9. So 1.8 and 53.9. Again I have to divide it by 2 pi FL. Okay, that's it. We are done with the values. Okay, so we have to fill out this table. We need secondary voltage, okay, secondary current, okay, secondary power factor. Okay, this is something new. The bad news is that Simulink doesn't have the power factor block, so we have to make our own block that can calculate the power factor. So if you remember, the power factor is calculated by real power divided by apparent power, and apparent power is basically the square root of real power square plus reactive power square. So we can implement this easily in the Matlab. We have this power block right here. So we will provide it V2 and I2. Then we have P and Q. So to implement this formula, we need square root, we need square block, and we need a divide block. Okay, go to the math operations. We need add block, divide block, square root block, and math function. Where is it? Math function, this. Okay, so we need p square plus q square. Okay, this is the math function, make it square. Okay, so we need p square, we need q square, and we need to add these together. And then we need to take the square root of this. So we have implement this thing, apparent power, p square plus q square and square root. So we need to divide this apparent power by real power. So this will divide, and no, real power divided by apparent power. So real power divided by apparent power. So we will get here the output, that is the power factor. This is the power factor. You can make a subsystem. Power factor block. So this is how we created our own power factor block. Okay, so now we are ready to. Okay, so first we have to find the no load voltage. So for no load voltage we have to remove this. We did not have power GUI block, so let's have a power GUI block. Here is the power GUI block. Okay. Okay, so the no load voltage is 120 volts. Now we will connect a load. Uh, 900 ohms. Okay. So this is how you will find the voltage regulation. Um, you will make after R, you will find out parameters, all these parameters for R and L load. To make R and L load, you will simply change it to RL load. That's it. And then for RC load, you will make it RC load. So do this for all these values, for all these parameters, and then fill out the voltage regulation and efficiency. Voltage regulation will be calculated just like this. This no load voltage is fixed that you have already found, 120 volts, and full load voltage is this secondary voltage basically that will change according to the type of load. So one thing that you will note that the voltage regulation will be different in each case. So you can say that voltage regulation depends the on the type of load. If it's R, then it will be something else, and if it's RL load, then voltage regulation will be something else. If it's RLC load, then it's something else. Okay, just to remind you that in practical we have uh, RL load. You know, every load that you see around yourself that is made of R and L. There is no capacitive load. Naturally, capacitive load does not exist. We always introduce the capacitive load just to compensate the effect of inductive load, that is uh, L. You know, we always introduce the capacitive load just to minimize the effect of inductive load because the power factor is always low for inductive loads, so that's why we add capacitors uh, uh, in parallel with the load so that the inductive load is minimized and our power factor gets improved. So you will notice that the voltage regulation might be negative for this case RC load. So that's normal. Voltage regulation can be negative if we have a capacitive load. So that's normal. RL load will have the poor, uh, the most poor will be the most poor voltage regulation will be in case of RL load, and the voltage regulation in case of capacitive load can be negative. So do not worry if you get a negative value in this case. Okay. Uh, as far as efficiency will be calculated by output power divided by input power. Through this formula, you can easily calculate the efficiency for each case. Practically speaking, the transformers are really efficient devices. The voltage, the efficiency can be as high as 99%. On average, it's around 95 to 98% normally, the average efficiency of a transformer. So transformer is really an efficient device. Okay guys, so that's it for this lab. Okay, one thing I want you to notice that you have already performed lab number 2 and lab number 3. So I just want you to notice that if you go into the properties of transformer, make it SI units. Okay, so then you will notice that this is the uh, shunt branch parameters of the transformer, 1.08 into 10 power 6. So this is basically RC, and this is inductance of the uh, shunt branch parameters. So the parameters that you got in lab number 2 and 3 will be similar to these parameters. Do compare these parameters with lab number 2 and lab number 3. Similarly, this is the R equivalent, 4.3 and 0.7. If you add them together, then it will be around 5 volts, and this is the corresponding inductance value. So do compare these values with the values that you got from lab number 2 and 3, and you will find out that uh, similar values, you have similar values. Okay, that's it from lab number 4. So do complete this lab, and we will meet in lab number 5. Okay.